Okay, welcome to this session where I want to show you our findings in the Z-level project where we looked at the fault handling test of a highly automated driving situation, and we selected an example where a specific component has a failure. Well, first of all, why do we have to do this? What are the objectives? Well, of course, we are required to do a robust design and a fault-tolerant system. And in automated vehicle, it must also be capable to handle subsystem faults. And these subsystems are not only those systems which are new if you have a automated driving, like a sensor, but also the traditional mechanical components like a tire or an actuator component could fail, and the automated system must be capable to handle this. So which simulations would we look at it if we do such an investigation? Well, first of all, we would do a test with the system in the original situation with no fault, and we would simulate it and check if the system is capable to simulate this at all. If not, we have to exclude this situation. It's not useful to test an error or a fault. Then we would simulate with fault and to check if the system is fault tolerant enough to handle the situation without any alteration. But if the system with a fault and without detection fails, then we would have to implement a fault reaction and again doing a test to check whether this implementation of the fault reaction is appropriate. So test number 3 would be simulating with fault and with detection and with reaction of the system. So that's our task. And now let's look at the simulation environment. Here you see the architecture, general architecture, more smaller part here now. We have the simulation core. Our system under test is the ego vehicle with the driving function, the motion control, and of course with the vehicle dynamics and actuator models. And we also have some agent models and sensor in this case. So what are the requirements on the system to be able to do these simulations? Well, first of all, this vehicle dynamic model and the components must be capable, must have the appropriate level of detail to be capable to simulate that. If you want to get more information about the vehicle dynamics and the component models, you can visit booth number B1-3, where this is the topic. And to simulate this fault injection, we have to add 2 additional signals. The one thing is a fault injection signal, which replaces the arbitrary time when this fault occurs in reality. In simulation, we want to trigger it at a specific point, so we have this signal additional going from the simulation core to the actuator models. And additionally, we have to implement the fault detection signal from the vehicle or from the actuator model to the rest of the vehicle, or to the head function in this case. And here we used an existing OSI signal, and we extended this OSI signal with the steering status or with the status of all the actuator models. In our case, it was the steering system. So these are the 2 additional signals we need. We tested this approach or architecture in one demonstration example, and you see here on the upper right corner. So our demonstration example was we assumed that a steering sensor is failing, and due to this failure, the steering system switches into a fault mode. And the fault mode in this case is that the speed of the steering actuator is limited. And as you can think, the most critical is this situation where the speed, how fast you can steer the vehicle, is most critical if you have a narrow curve. So we set up a traffic following traffic scenario. We have a small urban crossing, and the ego vehicle is doing a right turn. You see here this silver car, it's the ego vehicle which does a right turn. And we have additional obstacles. We have this truck here on the left, and we have a pedestrian here. And just going into the crossing, we assumed that the fault would occur and would limit the speed of the steering actuator, so the vehicle has problems doing this right turn in a proper way. So, and we already come to the results. So here you see some plots. Here you see the 3 tests again we had. Test number 1 is without any error. You see the truck here as the lilac curve, and the EO vehicle the blue curve, and vehicle which turns here right. And number 2 would be where the error occurs, and you see here large oscillation of the vehicle. Now we printed it red here, and you get very close to this pedestrian. And test number 3 is with detection of the fault and with reaction of the vehicle. And you see again the trajectory looks pretty much the same as here. And you can see it even closer if you plot all the trajectories of the Eco vehicle for all 3 test cases here, blue, red and green. You see blue and green are the very same, but if we have the fault without reaction, it's not reacting properly. And what is the proper reaction which we implemented? Well, the reaction is that you see here in the green curve, you look at the speed of the vehicle, it slows down as soon as the fault occurs, the vehicle slows down. So in slowing the vehicle down, then of course also the steering velocity is slower, which is required. And so the trajectory is basically the same, but the vehicle is going simply very slower. And the critical parameter we looked at is the side distance to the pedestrian. So you see, if we have red one again, the situation with an error, but without handling of the error, we are much closer to the pedestrian as in the original situation without fault, or with fault and with proper reaction to this fault. If you are looking on the online then you can also take a look at the video where you see even closer now the differences between the 3 different test cases. Thank you very much.